Okay, so you're here on the deep dive, and you know how this works, right? You want the core info, you want to get smart fast without having to wade through a ton of, fluff, and we're here for that. That's what
Yeah,
we do.
exactly.
So today, we're going to be looking at these really powerful tools, actually, and they might seem kind of basic at first, but I think by the end of this, you'll see how useful these can be. We're talking about measures of central tendency and measures of dispersion.
Yeah, in statistics, this is like fundamental stuff.
Yeah. And we've got some great resources that lay out all the formulas and the step by step how to do this stuff. But what we want to do in this deep dive is like really unpack those ideas. So they're not just something you can like calculate, by rote, but
Yeah.
you really understand what they're telling you about a data set.
Yeah, I think that's key because you can plug numbers into a formula, but if you don't know what those numbers mean, it's not really that helpful, is it?
Right? It's just like, going through the motions. And what we want is for you to like actually be able to look at data and be like, okay, I know what this means. Like I understand like what the story is behind these numbers.
Totally.
Okay, so let's get into it. I guess the first thing we should talk about is like, when you've got this pile of numbers, right? Like where do you even start?
Well, the first thing you often want to know is what's typical. Yeah. Right? Like if you've got all this data, what's the typical value? What's sort of the center point of it all? And that's where measures of central tendency come in.
Okay, so measures of central tendency, those are ways to figure out what's like the middle or the average. Yeah.
Exactly. And there are a few different ways to do that. The most common one is probably the mean, which is what most people just call the average.
Okay, so the mean, the average, we've all calculated that, right? You add up all the numbers and you divide by how many numbers there are.
Yep, that's it. The formula for that is xn, that little x symbol that just means sum of all the x's where x represents each individual data point, and then n is the total number of data points.
Okay, so let's say we're looking at like average movie ticket prices over time, right? Like we pulled data for 9 different years between 1980 and 2019 just to see how ticket prices have changed. And we found that in those years, the average ticket prices were $2.69, $3.55, $4.23, $4.35, $5.39, $6.41, $7.89, 3 cents, and $9.16.
Okay, so to find the mean ticket price, we'd add up all those prices.
Right. So if we add all those up, we get $52.10, and then we divide that by 9 because we have 9 data points in 9 different years, and that gives us a mean ticket price of $5.79.
So on average, across those 9 years, a movie ticket costs about $5.79.
Which, seems pretty good compared to today's prices.
Yeah, no, right.
Okay, so that's the mean. That's pretty straightforward. But what happens when we don't have a list of individual data points like that? What if we have like a frequency distribution?
Ah, yes. So a frequency distribution is where you have different categories or values, and you know how many times each one occurs. So instead of having a list of like, stress level 7, stress level 3, stress level 7, you have a table that says, stress level 7 occurred 31 times.
Okay, right. So like instead of listing out every single person's stress level, we just have a summary of how many people reported each level.
Exactly. And in those cases, we use a slightly different formula to calculate the mean.
Okay, so what's the formula for that?
It's 6s. So in this case, x still represents each data value, but now s represents its frequency, how many times it appears in the data set. So you multiply each value by its frequency, add all those products together, that's the 6f part, and then divide by the total number of data points in which you can find by adding up all the frequencies.
All right, let's try an example of that. So we looked at a data set on student stress levels measured on a scale from 0 to 10, with 0 being no stress and 10 being like super stressed out. And we had this frequency table showing how many students reported each stress level. So like 2 students reported a stress level of 0, 1 student reported a stress level of 1, 3 students reported a stress level of 2, and so on.
Okay, so to calculate the mean stress level using this frequency distribution, we'd start by multiplying each stress rating by its corresponding frequency. So we'd do 0 times 2 plus 1 times 1 plus 2 times 3, and so on, all the way up to 10 times the frequency of stress level 10.
Right, and if you do all those multiplications and add them all together, you get 975.
And then to get the total number of data points, we add up all the frequencies. In this case, the total number of students was 151.
Right, so we divide 975 by 151, and that gives us a mean stress level of approximately 6.46. So the average stress level for this group of students was about 6.5 out of 10.
Exactly. So even with a frequency distribution, we can still calculate the mean. It just involves a little bit of extra multiplication.
Right. Okay, so we've got the mean down. But you mentioned that there are other ways to find the center of a data set, right?
Yes, exactly. While the mean gives us a sense of the average, It can be a little misleading sometimes, especially when you have extreme values or outliers in your data.
Outliers, those are like the data points that are way off from the rest, right? Like if everyone's scoring around 80 on a test and then one person gets like a 20, that would be an outlier.
Exactly, and those outliers can really pull the mean up or down.
Hmm.
So to get a better sense of the true middle value, we often look at the median.
Okay, the media. So how's that different from the mean?
The median is the middle value in a data set that's been sorted from smallest to largest. So instead of adding and dividing, you just find the number that's right in the middle.
Okay, so like if we have the numbers 84, 90, 98, 95, and 88. First, we have to put them in order. So that's 84, 88, 90, 95, 98. There are five numbers, so the one in the middle is 90, so that's our median.
Exactly. And the key thing about the median is that half of the values in your data set are smaller than the median and half are larger.
Right, okay, that makes sense. But what if we have an even number of data points, like in this example? 68, 74, 7, 13, 15, 25, 28, 59, 34, and 47.
Yes. So when you have an even number of data points, there isn't a single middle value. So in those cases, the median is the average of the two middle values.
Okay, so let's put those numbers in order first. 7, 13, 15, 25, 28, 34, 47, 59, 68, 74. We have 10 numbers, so the two in the middle are 28 and 34. So we add those together, that's 62, and then divide by 2, which gives us a median of 31.
Exactly. So even though we have some higher numbers in there, like 74, the median is still pretty close to the middle of the pack.
Right, and that's because the median isn't as affected by those outliers as the mean is. Like that 74 doesn't pull the median up as much as it would pull the mean up.
Precisely. The median is more resistant to those extreme values, which can make it a more reliable measure of the typical value in some cases.
Okay, so the median is the middle value when the data is in order. Is there like a formula to figure out where that middle value is, especially if we have a really long list of numbers?
There is. The position of the median in an ordered data set can be found using the formula n plus 1, 2, where n is the total number of data points.
Oh, okay. So like with the nine longest words with lengths 25, 25, 27, 27, 28, 29, 29, 34, and 45, there are nine words. So 9 plus 1, 2 is 5. So the median is the fifth word in the ordered list, which is 28.
Exactly. And we can even apply this to our frequency distribution of stress levels. Remember, we had 151 total responses. So the median position is 151 plus 1, 2, which is 76.
Okay, so that means the median stress level is the 76th value in our ordered data set. If we go back to our frequency table and start counting up the frequencies, we can find that the 76th data point falls within the group of students who reported a stress level of 7.
Which means that the median stress level is 7. Notice how the mean stress level is about 6.5, but the median is 7. This suggests that maybe the distribution of stress levels is a little bit skewed towards the higher end.
Okay, so by comparing the mean and the median, we can start to get a sense of the shape of our data too. That's interesting.
It is, and it highlights why it's often helpful to look at both measures.
Yeah.
Now, to really drive home the point about outliers and how they affect the mean and median, let's look at an example with salaries. Let's say we have a small company with 5 employees earning $29,700, $30,400, $31,000, $32,600, and $33,000 per year. And then let's say the owner of the company earns a salary of $105,000.
Okay, so to find the median salary, we first put the salaries in order. $29,700, $30,400, $31,500, $32,600, and $105,000. There are 6 salaries, so the median is the average of the two middle ones, $31,500 and $32,600, which gives us a median salary of $32,050.
Right, so half the people in the company earn less than that and half earn more. Now let's calculate the mean salary.
Okay, so we add up all 6 salaries. That gives us $262,200, and then we divide by 6 because there are 6 salaries total, and that gives us a mean salary of $43,700. Whoa.
Yeah, you see how that one really high salary, the owner's salary, has really pulled the mean up?
Yeah, that's a huge difference between the median of $32,050 and the mean of $43,700. So it's like if you just looked at the mean salary, you might think, oh, this is a pretty well-paying company. But then when you look at the median, you realize, oh, actually, most of the employees are earning significantly less than that.
Exactly. And that's why it's so important to be aware of outliers and to consider using the median when you suspect they might be skewing the data.
So the mean is influenced by all values equally, while the median is more focused on finding the true middle value regardless of those extremes.
Exactly. Now let's move on to a measure of central tendency that's a little bit simpler. The mode.
Okay, the mode. I remember this one. The mode is just the value that appears most often in a data set,
I
right?
got it.
So like in a set of numbers 7, 2, 4, 7, 8, 10, the number 7 appears twice and all the other numbers only appear once. So the mode is 7.
Precisely. It's just the most frequent value. And it's worth noting that a data set can have more than one mode if multiple values tie for the highest frequency.
Oh, right. Like if we had another 2 in that set, then both 2 and 7 would be modes. And I guess a data set could have no mode at all if all the values are different.
Exactly. The mode is especially useful when you're dealing with categorical data, like favorite colors or types of cars where you can't really calculate a mean or median.
That makes sense. Okay, so we've got the median, and the mode. Are there any other measures of central tendency we should talk about?
Just one more. The mid-range. This one is kind of related to the range of the data, which we'll talk more about later, but essentially the mid-range is the midpoint of the entire range.
Okay, so how do we calculate that?
You take the smallest value in your data set, add it to the largest value, and then divide by 2. It's kind of like finding the average of just the two extreme values.
Oh, okay. So, like in that example we looked at with the 12 best countries for women, the scores range from 87.2 to 100. So, we would add those together 87.2 plus 100, which is 187.2, and then divide that by 2, which gives us a mid range of 93.6.
Exactly. So the mid-range is a very quick and easy way to estimate the center of the data. But it can be pretty sensitive to outliers because it only takes into account those two extreme values.
Right. If we had one country with a score of like 20, that would really drag the mid range down, even though most of the other countries had high scores.
Exactly. So it's important to keep that in mind when you're using the mid-range.
All right, so we've covered the mean, median mode, and mid-range. Those are all ways to find the center or the typical value of a data set. But what about the spread of the data? Like, how much do the values vary around that center point?
Ah, yes. That's where measures of dispersion come in. These measures tell us about the variability or the scatter of the data.
Okay, so if measures of central tendency tell us where the data is centered, measures of dispersion tell us how spread out it is.
Precisely. And there are a couple of key measures of dispersion we should talk about. The range and the standard deviation.
Okay, let's start with the range. We kind of touched on that with the mid-range, but what exactly is it?
The range is simply the difference between the highest value and the lowest value in a data set. It's the simplest measure of dispersion, and it gives you a quick sense of how much the data spans.
Right. So, like in that example we had with gasoline prices over 4 years, the lowest price was $1.17 and the highest was $2.79. So, the range is $2.79, which is $1.62. So, that tells us that over those 4 years, the price of gasoline varied by a total of $1.62.
Exactly. And remember the Honolulu temperatures. The highest was 89 degrees Fahrenheit, and the lowest was 61 degrees. So the range there is 28 degrees.
Okay, so the range is just the difference between the highest and lowest values. Pretty straightforward. But you said it's the simplest measure of dispersion, which makes me think there are more complex ones.
There are, and the most common one is the standard deviation.
Standard deviation. That one sounds a little intimidating. What's the basic idea behind it?
The standard deviation gives us a measure of the average distance the data points are from the mean. So think of the mean as like the bullseye on a target. The standard deviation tells you how tightly clustered the shots are around that bullseye. A small standard deviation means the data points are generally close to the mean, and a large standard deviation means they're more spread out.
Okay, so it's kind of like a measure of how consistent the data is. If the standard deviation is small, the data is pretty consistent. If it's large, the data is all over the place.
Exactly. Now, to calculate the standard deviation, we go through a few steps. First, we calculate the mean of the data set. Then we find the deviation of each data point from the mean.
Okay, so if the mean is like 10 and one of our data points is 12, the deviation is 2. And if another data point is 8, the deviation is -2.
Right. Now, if we were to just average all those deviations, the positive and negative values would cancel each other out, and we wouldn't get a good sense of the overall spread. So the next step is to square each deviation.
Okay, so squaring the deviation of 2 gives us 4, and squaring the deviation of -2 also gives us 4. That way we get rid of the negative signs, and we're just looking at the magnitude of the deviation.
Exactly. After we've squared all the deviations, we add them all up. This gives us the total squared deviation from the mean. Then we divide this sum by n1, where n is the number of data points. This value is called the variance.
Okay, so the variance is like the average squared deviation from the mean.
Pretty much. And then the final step is to take the square root of the variance, and
Yeah.
that gives us the standard deviation.
Okay, so let's go back to our gasoline price example. $1.17, 1.52, $2.79, and $2.80. We already found the mean to be $1.89. So the deviations from the mean are negative $0.72 in Exner of 37.90 and 19 cents, and that was in 19 cents.
Right, and if we square each of those deviations, we get 0.5184, 0.1369, 0.81000361.
Okay, and then if we add all those squared deviations together, we get 1.501 phi, and we divide that by 3 because we have 4 data points, so n1 is 3,
Yeah.
and that gives us a variance of about 0.50.
And then to get the standard deviation, we take the square root of 0.50, which is about 0.71.
Okay, so the standard deviation of those gasoline prices is about $0.71. So that means that on average, the individual gas prices were about 71 cents away from the mean price of $1.89.
Precisely.
All right, so to recap, we've got measures of central tendency like the mean, the median, the mode, and the mid-range, which all tell us about the center of a data set. And then we have measures of dispersion like the range and the standard deviation, which tell us how spread out the data is.
And by using these measures together, we can get a much more complete picture of the data than we would if we just looked at any one measure in isolation.
Exactly. So next time you see a statistic about like the average salary or the average temperature, don't just take that number at face value. Think about what kind of average it is. Could it be skewed by outliers? How much variation is there around that average? By considering these measures of central tendency and dispersion, you can really start to dig into the data and understand what it's really telling you.
Absolutely. And the more comfortable you become with these tools, the more critically you'll be able to engage with information, and the less likely you'll be to be misled by statistics.
So think about some data you've encountered recently. Maybe it's something you saw in the news or a report at work. How could these measures help you interpret that data more effectively? What story do they tell about the data that you might have missed otherwise?
It's really about going beyond the surface level and developing a deeper understanding of the information that surrounds us. And with these statistical tools, you have the power to do just that.
So get out there and start analyzing.
Have fun with